Okay, so hi everybody. It's a great pleasure for me to introduce the speaker of today, who is Rishikesh Fulari. Rishikesh graduated this year from Purdue University for Twain. He was in the Department of Computer Science and he worked with me in the Laboratory of Science for some time. Now he's at William Blair, so it's a great pleasure for having him being back here and hearing what he has to say about physics in for neural networks and monotonicity. Rishikesh, the stage is yours.
Yeah, thank you so much, Professor, for having me here. And I'm delighted to present my research at Purdue University through this session. Mm. So I will share my screen, and is my screen visible? Okay. So uh, I will first go through what machine learning is about and what deep learning is about. Then we will slowly move to pins and finally to pins with monotonicity. The reason I'm following this approach is because deep learning is built on machine learning and pins build on deep learning, and pins with monotonicity will of course first need a short overview of what pins are about. So this is the approach that I will be taking in this session so that I can explain it better and you too will find it more easier to understand. So first of all, I will go through all the slides, the presentation that I have, and I will cover the conceptual understanding of physics-informed neural network. And towards the end of the session, I will show the code that I have used for implementing all the research that I'm talking about. And eventually, I will display the report, the research that that I conducted under the Professor Alessandro, and the findings of our research and the key takeaways. Okay, so let us start. So machine learning. So what is machine learning? Uh, to put it in simple terms, when we talk about machine learning, it's just a mathematical equation that represents certain traits or patterns. Like everything around us is governed by certain patterns, or we can say traits. Like everything that is happening around us, if we can quantify it, if we can measure it and put it in the form of numbers, then it is highly likely that we can fit in some mathematical equation on top of that. And that is exactly what machine learning is about. So we have a set of values for x, and then we have some output values for y, and the goal of machine learning is to find that one function f that maps those input variables in x to the output variable y. Now, when we talk about patterns, they are everywhere. Currently, I'm working with the investment banking company, so most of the patterns and projects or case studies that I come across are financial ones. Like for example, take the case of stock market. So even though we are not able, like we cannot like perfectly quantify the predictions for stock market, but we can still estimate the trends that occur in stock market. Similarly, the company decisions that are taken by the leadership, by the people in authority. So those decisions are largely driven by data, and by data I mean data science and machine learning. For example, their decisions to say acquire a company. Suppose a private equity fund wants to acquire a company, then this decision will largely be based upon their past deals, their historical data. Similarly, say there are like millions of financial transactions that are happening every day throughout the world, and a small fraction of those transactions are fraudulent, uh, which are done by scammers to scam innocent people. But even in those fraudulent transactions, there are some particular patterns that we can find. And the goal of machine learning is to uncover these kind of patterns. So one thing that I'm trying to put forward here is that everything that has some pattern can be replicated, can be demonstrated using machine learning. We can find, if we can quantify it, then if we can measure it, then we can put it in the form of some x values and corresponding y values, and we can fit a mathematical equation on that. So that is what machine learning is all about. And these are like there are myriad of applications of machine learning. I think there is rarely a domain or an industry where machine learning wouldn't have any application. Be it even the climate change. There are like open source projects that are working in the climate change domain. Then there are financial markets is one another application. Then internet, tech. These are all different applications of machine learning. So now let's like I will narrow it down to one like specific case study. I can say a simple case study to understand the classical machine learning models that we are talking about here. So, for example, you are working for a company and you want to predict what your salary increment will be after say year or say couple of years. Now, your salary increment will largely depend upon your performance, on your current salary, and on your manager's rating, like how your manager is rating your work. Is it satisfactory or not? And how your colleagues are rating your work. So, say, like these are the we are assuming that these are the three primary factors we can say which will determine your salary increment. So, if I assume that those three variables, say current salary, manager's ratings, and colleagues' rating, uh, are linearly related to each other, and y, which is basically your salary after 2 years, is the target variable that we are trying to predict. So we can create a simple mathematical equation here, which will be y is equals to x1 into w1 plus x2 into w2 plus x3 into w3, where w1, w2, and w3 are the weights, x1, x2, x3 are the variables. Now, using the past data, we can put in values of x1, x2, x3, and we can initialize the weights randomly and calculate the predicted value. And then we can iteratively, like using an algorithm such as gradient descent, we can find the ideal values of our weights. Of course, we will have to calculate the loss first and then accordingly use gradient descent on it. So this is how machine learning works, and it works pretty well for simple functions such as this one that we just looked into. But there are some applications like uh, for some mathematical equations which are way more complicated. Like, say, for example, in this case, we had made a simple assumption that those input variables x1, x2, and x3, those are uh, linearly related with our output variable, which is y. But imagine if those would have been related exponentially or parabolically or elliptically, or what if they would be following a sinusoidal wave? So, the equation that we are trying to find out or we are trying to fit in can be a lot more complicated than a simple linear equation that we just looked into. So, how do we represent such equations? So this is like one of the limitation of classical machine learning algorithms like linear regression, that they cannot represent highly sophisticated or very complicated mathematical equations. And that is where deep learning comes into the picture. So why do we need deep learning? So we need deep learning so that we can demonstrate or we can like compose or represent complex mathematical equations. Now, what is deep learning and how it works? We will look into this now. So when we talk about neural networks, we can start with perceptron, which is very, very similar to the linear regression model that we just saw. So here it's we have x1, w1, x2, w2, x3, w3. We are summing it up, and on top of that, we are putting on some function, and this becomes the perceptron, which is like the smallest unit of neural network. So the way deep learning works is that we stack those perceptron like neurons one on top of each other, and we use a lot of them, and that is how we get a deep neural network. Using deep neural network, we can actually represent highly complicated functions, like highly complex function that are not linear but say elliptical or parabolic in nature. So this is the advantage of deep learning, that we can represent uh, complicated equations. Uh, and how does deep learning work? So it works in a fashion very similar to the one that we just discussed before. So we will have some input variables, we will randomly initialize weight, and then we will calculate the predicted value. We will calculate the loss, and using back propagation, we will update the weights going backwards using differentiation. And, and that is pretty much how we will be doing it on iterative basis. And that is how we will get the ideal weights for those functions. So this is basically how deep learning works. Uh, so the advantage of deep learning is that it can represent complicated functions, complicated mathematical equations, which wouldn't have been possible using classical machine learning algorithms. But now the question is this enough? Uh, like today we are seeing generative models around us, which are basically sophisticated and a lot more powerful or complicated versions of the same neural networks. But then on the other hand, we also have some phenomena such as wave propagations, or we have a set of equations called as diffusion equations, or which are basically differential equations. So how do we represent differential equations? Are deep learning neural networks or machine learning networks enough for them? Uh, well, indeed, we can, but they won't be doing a great job at it. So, this is where physics informed neural networks come into the picture. We will try to understand it using, say, an example. So, imagine a metallic rod, and now imagine two candles. If I lit those two candles and put them at the either of the ends of like both the ends of this metallic rod, what will happen is that the metallic rod ends will start heating up, and slowly, with passage of time, that heat will travel towards the center of the rod. So, a simple phenomena actually. We have a metallic rod. We lit candles at both the ends of that metallic rod, and both the ends of the candles started heating up. The heat, with passage of time, slowly propagates towards the center of the metallic rod. Now, do you think this process is happening randomly? No, it's not. It is kind of a systematic process that happens, and we can actually represent this phenomena, or we can represent everything that is happening here in terms of equation. The difference is this time it's not some simple equation, but instead a differential equation. The one that I have mentioned here, like du by dt is equals to k into d u square upon dx square. So basically, if x is say represents the length of the rod, so dx will be a small change in the length of that rod, and dt is like the time, and dt is like the small minuscule amount of time. So here through this equation, we are trying to represent how the heat will propagate and how it will impact, like how much heat will be propagated over the length of the rod and in what time. So that is what this equation is representing. So if we are to solve this kind of equations, or if we are to simulate this kind of equations, now here I'm slowly moving from solving equation to simulating equations, because when we talk about differential equations, we don't really have exact solutions. So the only way to understand them or study them is by simulating those equations, by creating a set of solutions that behave in a manner similar to the one represented by the equation. So if we are to solve it using numerical methods or mathematical methods, so this is how we will go about it. We will have an x value, we will have a dx. Uh, Basically, we will take the double derivative and the first order derivative of those equations, and this is how it will look. But now that it is a relatively simple equation, we might find numerical solutions to this by defining some boundary conditions for x and t. But here, for the sake of understanding, I have taken a simple equation, that is the heat equation. But there are certain equations such as diffusion equations that we will be delving deeper into now, that are lot more sophisticated and lot more complicated and cannot easily be represented or efficiently simulated using uh, deep learning models. And this is exactly where physics informed neural networks come into the picture. So why do we need pins? We need pins to simulate differential equations which otherwise wouldn't have been easily be able to be simulated using deep learning networks. And how are exactly those pins that we are talking about, like physics informed neural networks, different from the deep learning neural networks that we talked about? So physics informed neural networks are actually a subset of deep learning neural network, where the primary difference lies in the loss function that we use. So uh, generally there are like a couple of differences we can say. The differences are that uh, in physics informed neural network, we have some initial condition, we have some boundary conditions. We work on a small domain of data. So we basically restrict ourselves to a small subset of data, which are defined as the initial conditions or the boundary conditions. And the another difference uh, is about the loss function component. In deep neural networks, we will have a loss function such as, say, mean squared error or cross entropy loss or root mean squared error or absolute mean squared error. But in uh, physics informed neural network, in addition to these laws, we also have another loss component, which basically ensures that we are representing that particular mathematical equation, that differential equation that we are trying to solve. And how would that component be? Like, for example, in this case, if I have to represent, or if I have to create a physics informed neural network for this particular equation, then what I will try to do is I will try to subtract the right hand side of the given equation here from the left hand side, and I will try to make the absolute difference between the LHS and RHS here to zero. In neural networks or even in simple linear regression, if you have noticed, we do have a regularization term. So Even this function, you can think of it as a regularization term where we are trying to minimize the difference between the right hand side of the equation and the left hand side of the equation, and we are trying to basically make it equal to zero. So this is the added component in physics informed neural network, which we wouldn't find in deep neural network. Now, what are the advantages of this approach? So one primary advantage of using physics informed neural network is that unlike deep neural network, it does not require like thousands or like 10,000s of or millions of records. In physics informed neural network, we generally work over a small subset of data, which can and which is most of the times synthetically generated. We don't have to rely on empirical data that has like thousands or tens of thousands or hundred of thousands of rows. We can actually synthetically generate data for training physics informed neural network. We can define our initial conditions, we can define the boundary conditions, and with just a small set of data, say 100 records or even 150 or like 200 records, we can actually train the physics informed neural network, provided our data set size is big enough, like greater uh, than the number of trainable parameters that we have in neural network. But note that even though the overall dataset size that is required for pins will be considerably smaller than what we might require when we use deep neural networks. Now, how we use pins? So, we generally use physics informed neural networks to represent, to simulate differential equations, such as diffusion equations, uh, be it heat diffusion or air diffusion, gas diffusion basically. So we do have numerical methods into existence which can solve or which can simulate those differential equations. But not all differential equations are easy to be numerically represented or numerically solved or simulated. So in such instances, in such cases, physics and for neural networks come to rescue. We can use pins to simulate these equations. And that is like one of the core or one of the important applications of pins. Now we are actually delving into the research that I conducted. Now that we have gone through machine learning, deep learning, and pins, now let us discuss about one particular application of pins that I worked on during my research phase at Laboratory of Data Science. So it was with Fisher KPP equation. So it is a type of diffusion equation. Uh, so let us try to understand what this picture here and this equation here is about. So one thing to note here is that, see, as you can see, this wave representation here has three axes. The first axis is the time, which goes all the way from 0 to 15. The another axis that we have is x, which goes all the way from -25 to 50. And the third axis that we have is the u, which is like the actual value of the function, which actually represents the function. So note that at t equals to like at x equals to 0, the value of u is 1 over the entire time period from t is equals to 0 to t is equals to 50. Point number one, this is like the point number one. The another point to note here is that at x equals to 50, from t equals to 0 to t equals to 50, like throughout the overall period of time, the value of u is 0. These 2 points actually form the initial conditions of our physics informed neural network. So when defining a pin, we actually need to put in boundary conditions and initial conditions, and this is exactly what it is. So the two points that I just mentioned form the boundary conditions of our overall equation. So the way this wave propagates is that it's a step function and it will propagate to form a smoothly decreasing function. So this is the wave propagation, like from step function to a smoothly decreasing function. And we are to simulate this wave propagation. So note the initial state, which is a step function, like a two-step function, and the final state, which is a smoothly decreasing curve. So note this initial and the final state because this is what we are trying to simulate using pins. And this is the equation that represents it. Here D and R both are constants. U is the actual function that gives us the value of how this wave is propagating with respect to time. The differentiation here, du by dt and d square u by dx square, give us how this wave is changing with respect to time and distance. Now coming to the next slide. So as you can see here, so this is the graph that I generated using physics informed neural network. So what I did is I tried to replicate the wave that we just see here, that the one that we have just seen here. I just tried to replicate it using physics informed neural network. And these are like kind of the graphs that I achieved where it is like kind of a step function and then it translates into this kind of function, a decreasing function. But note that here you will observe small bumps and so are here. Ideally this function should have either been constant, the final function I mean, this should have either been constant or just decreasing. It shouldn't have shown an upward bump, and that is what the problem is. So while simulating this wave propagation, this is the problem we are facing. Now, before going forward, I want to introduce this term called like monotonicity or monotonous functions. Like what are monotonous functions? So monotonous functions are they can be of two types. The one is like monotonously increasing or monotonously decreasing. Monotonously increasing functions are those which will either stay constant or they will continuously increase, but they will never ever decrease. So such type of function we call them monotonously increasing functions. Then we have monotonously decreasing functions where the function will either stay constant or it will be continuously decreasing. So this type of function we call it monotonously decreasing function. Now here, if you observe that this function should ideally have been a monotonously decreasing function. There shouldn't have been a upward bump that we have. So here, what we did in particularly in our research is we added a component, a monotonous loss function, inspired from epidemiology informed neural network, which is another type of neural network. So here we have tried to include another loss term that basically penalizes penalizes the model when it tries to be a non-decreasing function. So it is a decreasing, monotonously decreasing function, and that is how we want it to be. We don't want those bumps. We don't want it to increase, and therefore we added one monotonous loss component to the to our loss function. So see, here is how we went with it. First, we had a simple loss, like as we the kind of loss that we see in machine learning, like root mean squared error or mean squared error. Another loss component we added was of physics informed neural network, which was you can call it a physics loss or kind. And the third loss component is the one that we are adding now, which is for the monotonicity, to ensure that the function is monotonously decreasing. So this is the loss function. Now this is not the exact loss function that we are using. We kind of are using a different version of it, but we were motivated or like inspired like from this loss function that we got from epidemiologically informed neural networks. When we add a monotonous component to our equation, monotonous loss component to equation, this is the graph that we give. Now here you can see that this graph is a lot more smoother than what we had got previously. Even like, and this is very similar to the graph we had seen here. If you can observe the final state of wave here, the graph that we have got now is very similar to that. And this is like a key finding or the key contribution towards physics informed neural network of our research, that we have added a monotonicity loss component to the loss, to the overall loss of the physics informed neural network, and made it more efficient for simulating complex wave equations like such as diffusion equations. In our case, it was Fisher KPP equation. So uh, this was about physics informed neural networks with monotonic loss. Now I will briefly take you through the code that I have used for this. So this is the code that I used. So this is the simple neural network. So we experimented with different types of neural networks. By different types of neural network, I mean shallow neural networks and deep neural networks. So we used neural network that were like 2 to 3 layers deep, and we also used neural network that were like 6 to 7 layers deep. Uh, so these were like two variants of neural networks that we tried with. This is the step function. If you remember, when I was showcasing the graph, I said we need to define initial condition for our physics informed neural network. And this is exactly what we are doing here. So we are defining the step function which will define the initial conditions of our physics informed neural network. And this is the code for the actual neural network that we are building. Here, this is dx and this is dt. So here is the thing: the more, the smaller the value of dx is, the more accurate predictions you will get. The better will be your simulation of your wave. But the computations too will increase linearly. The more complicated your equation is, the smaller the value of dx and dt is, higher will be the computation that you will require. Here I am preparing the input using x and t. Here I am defining the boundary conditions, and here is the initial condition that we talked about. I am clubbing, like creating a matrix representation of the input. Mm, this is some performance based code, and here I'm using ADAM optimizer to optimize the neural network loss and mean squared error loss. So note that this is our first component of our loss, which is mean squared error loss. Now here we are doing some back propagation, and as we come here, now this is the code that I want to draw your attention to. So here we are defining another type of loss, which is the differential equation loss. So see here, this is the right hand side of the same equation, Fisher KPP equation, and this is the left hand side of the equation. And we are trying to minimize the difference between the LHS and RHS, trying to make it zero. And this loss component is what makes the neural network a physics informed neural network. The rest of the implementation is similar to a typical neural network that we would have using PyTorch. Something that is actually creating the difference here is this loss function right here. Then we have monotonicity loss. Uh, this is another component that we talked about. So this monotonicity loss component here is derived from epidemiologically informed neural networks, and we are defining it here. And this is our final loss function. So this is like the neural loss, uh, and this is like the differential equation loss, and this is our monotonic loss. Together, they form the overall loss, and this is how this neural network will be trained. We also added coefficients to those losses so that we can experiment with different variants of this loss. Like just like in logistic regression or linear regression, we have L2 regularization, and then we have a hyperparameter that we can train. Similarly, those coefficients are kind of hyperparameters for this loss function that we derived, and the rest of the code is trivial. It is similar to any neural network code. So I just wanted to highlight this loss function, and specifically the monotonic loss component that is our contribution to the physics and from neural network loss. So we conducted this research, and this was the final report that we generated. Like as I said, the boundary conditions are that x belongs to -20 to 50. Time will vary from 0 to 15, and dx by dt will be zero point 0.1. And these are the different graphs that we got. Like we experimented with one step initial condition function, shallow network, deep networks, shallow network with monotonous loss component, deep network with monotonous loss component, then two-step functions. So these are all the different graphs that we got, that we experimented with, different variants. We also tried with three-step initial function, and these are the results that we got. And this can also be implemented not just to step function, but we also tried with continuous function. And these are like kind of the results that we got through it. So yeah, so this was about physics informed neural network and the monotonic loss component, which was our contribution towards this research. And yeah, thank you for giving me this opportunity to present, and I'm open for questions.
Okay, so thank you very much for the great presentation, Rishikesh. So maybe just a small thing, right? So how difficult was to tune the hyperparameters of the model?
So generally in deep neural networks, we don't really have hyperparameters much, but the hyperparameters that we specifically added in this research, like the loss functions ones. So for that, I had to manually try different values of it. So basically, the report that I generated was the result of different values of coefficients, which were our hyperparameters in our case that I tried. So I think there was no other way out. I had to like manually try each of them, like different variants. Of course, I had to limit myself to some particular range, like maybe from 0.001 to 100. So I manually filled in those values, and that is how I experimented with them.
And then you show us in the report one thing which I think is also good to mention is that there are some negative results as well, which are related to maybe tuning of parameter, but also related to situations in which you impose monotonicity where it's not there, and then you do things worse than they actually are. But so that's very good. Okay, so well,
Yeah,
thanks a lot for your time and for the great presentations on physics in formula networks. So thank you very much for your time and for the great talk.
thank you so much. Thank you so much for having me. It was a really wonderful opportunity.
Thank you. Thank you.